Hi chemistry students, let's talk about reactions again, but we're going to look at them in a little more detail and not have the simple situation where we know if something is in excess. So we're going to talk about what's called limiting reactants today. And let's start with a little exposition of some carbon atoms reacting with an oxygen molecule to make carbon monoxide. And what I've got here is a stack of carbon atoms and a stack of oxygen molecules. So let's go through one at a time and imagine what happens as this reaction progresses. So first off, two carbons and one oxygen molecule can create for us two carbon monoxides. If we allow that to happen over and over and over again, at some point we're going to run out of either carbon or the oxygen molecules. So let's see what happens. One step at a time, we can imagine this occurring, and at some point we're going to run out of something. And in this case, we ran out of carbon. There's no more carbon left. We've made all the carbon monoxide we can make, and there's still a little bit of oxygen hanging around. In this case, because we ran out of carbon, it is limiting how much products we can make. It's limiting the reaction, so we call it the limiting reactant. It's pretty easy to see what the limiting reactant is when we have at our disposal small amounts where we can just visualize it. So by inspection, like we just did, we could figure out what the limiting reactant is. The challenge, though, is what do we do when we have arbitrary mass amounts which aren't telling us how many straight up? We've got to calculate that. And we don't know. We don't have a visual idea. So what we need to do with this little video today is actually determine a way to calculate the limiting reactant, given the starting amounts. And the way we're going to do this is we're going to start off by talking about a very familiar food item called a turkey sandwich. And our little turkey sandwich will be made of turkey on rye bread and with a big slice of cheese. So I just want you to imagine this scenario where we've got at our disposal 9 slices of rye, 5 nice stacks of turkey, and 3 thick slices of cheese. How many sandwiches can we make? So I'm sure almost immediately all of you said, well, I can make 3 sandwiches. And that's exactly right. You can make 3. You could identify that the limiting reactant in making your sandwiches was the cheese. So how did you do that? What in the world went on in your mind when you did it? Well, it starts off by, we need to now turn this whole making of a sandwich into a chemical-like problem so we can see a methodology. What we'll do is we'll write our how to make the sandwich, our procedure, as a reaction. Oh, we need 2 slices of bread. We need 1 stack of turkey, 1 slice of cheese, and then we can make 1 sandwich. Once we have that, you probably went along and did a little bit of math. Now, you didn't even realize you did this math, but let's see if this makes sense to you. First thing you did is you said, I've got 9 slices of bread, 9 slices of rye. And for every 2 slices of rye, I can make 1 sandwich. And so your mind said, okay, that makes 4.5 sandwiches. And then you went on to the next ingredient. Oh, 5 slices or 5 stacks of turkey. Well, each stack of turkey can make me 1 sandwich. So I can make 5 sandwiches from this. And then finally, you looked at the available cheese. You said, hey, you know what? I've got 3 slices of cheese. For every slice, I can make 1 sandwich. I can make 3 sandwiches. And you said, you know what? I'm going to run out of cheese, and I can't make all my sandwiches. So the only thing I can do is make 3 sandwiches. So that's what you did, and this is the mathematics we need to do in our limiting reactant problems. We're going to need to do exactly what I just did down here at the bottom, but for our actual molecules and atoms involved in the reaction. Let's see a little bit more before we go on. So first off, the limiting reactant is this reactant which limits how much product we can make. And we want to calculate this, and we just saw that it's the actual reactant which produces the least amount of product. This is often confusing for people because it's the limiting, but remember, limiting is the lower, it's the least amount, so it makes the least amount of product for us. So the calculation we're going to do is going to tell us the most we can make of that product. Why is it the most we can make? Because we've run out of one of the reactants. So if we have some kind of generic reaction, like right here, A plus 2B plus other reactants goes to C plus 3D plus possibly other products. The way we're going to go about doing this is we're going to choose one of the products to focus on. Normally, the problem that we're asking you will tell you which one is important. But the key thing is to just choose one. And then we're going to do a calculation to find out how much of that stuff can be made. Now, by how much, we may be asking how many moles, or we might be asking how many grams. Whatever it is, go ahead and just calculate how many you need in the proper set of units. So we're going to go from each reactant, and starting with the amount of A that we have. So someone's going to say you've got 3.7 grams of A. You're going to calculate how much C can be made from that. And similarly, then you'll start right away and you'll do the same thing for B, and you'll do the same thing for any other reactant, and you'll keep doing that, and you'll find out how much C is made from each reactant. And the calculation that shows the least amount of C that is produced, that's your limiting reactant, and it also tells you the maximum amount of C that can be made. These are great instructions. However, it's best to see this as an example within a real type of setting, the kind of thing you're going to see on the exam. So let's take a look at one. So here we go. We have the combustion of benzene. So we're going to burn benzene, C6H6, right here it is. We're going to burn that. That means we're going to react it in with oxygen, and it's going to produce for us carbon dioxide and water. And we're just going to imagine that someone has 100 grams of benzene and 99.99 grams of molecular oxygen. The molecular masses are given here because we don't need to waste time on that. The question is, how much water can we make? What mass of water? So our answer needs to be in grams or kilograms, something like that, even milligrams, but it doesn't specify, so just go to grams. So the first thing we do is we choose our reactants, and we do a calculation with each of them to find out how much water we're actually going to make. Let's start it off. So remember, focusing on water, so make water what you do as your computation. And we're going to begin by computing the mass of water that the benzene can make. So we start with this. We're going to write down the number of grams of water we can make from benzene. We're reminding ourselves that we don't know which one of these is the correct answer by adding this. Hey, here's how much water we can make from the available benzene. We start off, we've got 100.0 grams of benzene, and the molecular mass allows us to go from grams to mole. Just to remember, I got this from the periodic table, no place special, all right? So I'm now at, if you look carefully, I'm now at moles of benzene because the grams of benzene here and the grams of benzene here have canceled out. And now I can convert using the reaction, because the reaction tells me that for every 2 moles of benzene, I can make 6 moles of water. So now I'm sitting at moles of water, and for every 1 mole of water, that's 18.02 grams, and voila, I can run this calculation, find that there's 69.20 grams of water produced in this reaction if we were to use up all the benzene. However, I'm not sure that I'm going to use up all the benzene. I might run out of oxygen first. So let's do that calculation next. We now need to find out how much can we make from the available oxygen. So how many grams of H2O we can make from oxygen? We've got 99.99 grams. We convert that to moles. Don't forget, this is molecular oxygen, O2, so we need to use its full molecular mass, 32 grams per mole. For every 15 moles of oxygen, I can make 6 moles of water. That's according to the balanced reaction above. And then once again, for every 1 mole of water that I produce, that's going to have a mass of 18.02 grams, and I can produce only 22.52 grams of water. So from these two, we can see that the most we can create is 22.52. Why? Because we're going to run out of oxygen at that point. Once we get, and we've made 22.52 grams of water, there will be no more oxygen. There'll be a whole bunch of benzene left over, but that's not what we're asking here. We're asking how much water can we make, and our limiting reactant then is oxygen, O2. Maximum yield is 22.52 grams, and sometimes this maximum yield of 22.52 in this particular case is sometimes called the theoretical yield. So the maximum yield, theoretical yield, that's the same thing. All right. Let's do another practice problem where we have 111.11 grams of nitric acid. They're going to be reacted with 101.11 grams of sodium carbonate. Similar numbers, not quite exactly the same. And we've got nitric acid and sodium carbonate. And later on in your career, you'll find out this is an acid-base reaction. You're told that this makes water, carbon dioxide, and sodium nitrate. How many moles of sodium nitrate are formed in this reaction? To do this, you need to first balance the written equation. And since you're given the reactants and the products, you should write them down and then balance them. So here's my nitric acid. Here's my sodium carbonate. Here's my water, my carbon dioxide, and my sodium nitrate that's produced from this reaction. Once again, I'm asked how many moles of sodium nitrate, so my calculations should focus on making sodium nitrate. So just so you have these handy, here are the molecular masses of sodium carbonate and nitric acid, because we'll need those. Now what we need to do is compute the number of moles of sodium nitrate formed. I don't need to go to grams. I was asked about moles. All right, so make sure you read the question. That's one less step I have to deal with. So let's go ahead and find this. The number of moles of sodium nitrate from nitric acid. I started off the exact same way as I did in the previous problem. What I'm looking for and which reactant I am dealing with. Put my reactant in there, converted it from grams to moles, and then did the mole to mole conversion based on the balanced reaction to find the number of moles of sodium nitrate that could be produced. I'll do the same exact thing now, starting from the other reactant, which is actually not sodium nitrate, it's sodium carbonate. So there we go. So here we go, sodium nitrate from the sodium carbonate. We've got 101.11 grams of this stuff. Convert it to moles using the molecular mass, which I get from the periodic table. Use the balanced reaction to convert from moles of sodium carbonate to moles of sodium nitrate, and I find I can make 1.908 moles of sodium nitrate. So real quickly, you should be thinking in your head, which one of these is the limiting reactant? And I'm hoping your answer was nitric acid. And then you're saying, how much can I make? The most moles I can make, the maximum yield is 1.763 moles of sodium nitrate. So there we go, the limiting reactant, nitric acid, and we can make only 1.763 moles are formed. All right, so there's one more aspect to all this, and that is reactions are not perfect. While we write a reaction, we often think of it as it going all the way to completion, where every reactant gets used up, and that's what stops the reaction from ending. That's not necessarily the case, and it's very rare. There's many reasons why a reaction may not go all the way to the end. One is there might be imperfections in your sample, so it may not be 100% pure, which means some of your mass that you've actually put in there is not a reactant at all. It also could be that your reactants can do more than one type of reaction, and there's also, you would call these side reactions as something that you can, these side reactions are actually just something that's not going to produce your product, but something else. So you'll end up with less product than you expect. There are also some reactions just don't go all the way to completion, and they stop somewhere midway, and that's a whole process, a whole concept called equilibrium, which will be discussed in later classes of chemistry. So here's what we've got. We've got a reaction then that doesn't go all the way to the end. So we're going to do experiments to find out how much it actually does create of the product. So we have an expected amount, a theoretical amount that we can calculate. Then we can do an experiment, and with that experiment we can find out its actual amount. So we're going to call these amounts that are made, we're going to call them yields. And we're going to say we want to determine what the percent yield is for some reaction. So the percent yield will be defined as the actual amount we get from experiment divided by the amount that we actually calculate from theory, which is what we've just learned to do in this video, multiplied by 100. At that point, we can just do a real simple calculation. So for example, suppose in the previous experiment that we talked about on the page before, only 1.452 moles of sodium nitrate were made. What's the percent yield? Well, pretty straightforward. We only produced, in reality, 1.452 moles. we theoretically could create 1.763 moles from the available starting materials. So if I take that ratio, multiply by 100, I find out that there's only 82.36% yield for this particular reaction. So there you have it. There's some limiting reactant ideas, some examples for you, and a discussion of percent yield.